Lesson 2. In Plate 1, an automobile is traveling up and down some fairly steep hills. You are the driver and are cruising at approximately 45 miles per hour. If you should put your hand out the window while in position number 1, from which direction would the wind be coming? It is coming directly toward you. Where would the wind be coming from if you were climbing up the hill as in position number 2? It would still be coming directly toward you. As a matter of fact, no matter whether you're in position number 3, 4, or 5, the wind would always be blowing opposite to your direction of travel. This apparent wind, caused by your motion through the air, is called the relative wind. Of course, as you travel faster, the relative wind appears stronger. Anytime you move through the air, the relative wind becomes apparent. Plate 2 shows 2 more cases where the relative wind becomes very apparent. Remember, the relative wind always opposes your direction of travel. Look at Plate 3. If you go up, the relative wind comes down. If you go down, the relative wind goes up. This applies to cars, airplanes, trains, boats, anything that moves. Quite often, however, it is possible to find yourself traveling in one direction, but pointing in another. Plate 4 shows an automobile that has just skidded off a slippery road onto an area covered with ice. The car is out of control. It is pointing in one direction, yet traveling in another. In such a case, where would the relative wind come from? The direction in which you're pointing, or the direction in which you're going? The relative wind always comes from the direction in which you are traveling, not necessarily from the direction in which you are pointing. Plate 5 shows 2 different circumstances. In case 1, an airplane is pointing and traveling in the same direction. The relative wind, therefore, is coming from straight ahead. You might say that the airplane is attacking the relative wind head-on. In case 2, the airplane is mushing or slow-flying. It is pointing upwards, but is actually still maintaining a horizontal flight path. The airplane is now attacking the relative wind at an angle. This angle between the airplane and the relative wind is called the angle of attack. Plate 6 shows the airplane in various attitudes and with various angles of attack. The dotted lines represent the actual flight path of the airplane. The dashed lines show where the airplane is pointing. Study these figures for a moment and try to visualize each case. Which figure has the largest angle of attack? Which figure has the smallest angle of attack? Plate 7 shows another airplane with a high angle of attack. You'll notice that the angle of attack is measured between the relative wind and the chord of the wing. This is the true definition of the angle of attack. The angle between the relative wind and the chord of the wing. Since the chord of the wing is usually parallel to the center line of the airplane, the concept of the angle really hasn't changed very much. You may continue thinking of the angle of attack as the angle between the relative wind and the direction in which the airplane is pointing. Plate 8 shows a wing at a relatively high angle of attack. You'll notice that at high angles of attack, the wing creates a narrower area for air to flow through. Because of the decreased space for the air to flow through, the air naturally speeds up even more than it normally does. This increased airspeed over the wing creates even more of a low-pressure area, and hence the wing develops even more lift. Therefore, we can say that a wing will develop more lift at high angles of attack than at low angles of attack. In Plate 9, you'll notice also that at high angles of attack, the wing is not aligned with the relative wind. Therefore, there is bound to be more air resistance. More air resistance means a drop in airspeed. Now, here is one of the most important rules in flying. When you increase the lift of an airplane, the airspeed must go down. Or vice versa, if you increase your airspeed, you will lose lift. The only way to increase both is to have more available engine power. Now, we know that as we increase our angle of attack, we will increase our lift and lose some airspeed. This is true to a certain point. Plate 10 shows a wing at an excessive angle of attack. When a wing is at such a high angle of attack, the air is not allowed to flow smoothly over the top of the wing, and as a result of this, the wing will lose most of its lift. This condition occurs in any airplane when the angle of attack becomes excessive. The wing will lose its lift. This occurrence is called a stall. Now, many novices believe that a stall is an engine failure. In a car, this may be so, but not in an airplane. A stall is a condition where the angle of attack is so high, the air is not allowed to flow smoothly over the top of the wing. And without this smooth air flowing over the wing, there can be no lift. Plate 11 is a very interesting graph. The graph shows various amounts of lift for various angles of attack. At a 10-degree angle of attack, the lift is greater than the lift at 5 degrees. You'll notice that as the angle of attack is increased, the lift increases. You can see that when the angle of attack reaches about 20 degrees, there is a sudden loss of lift. This is the point at which the stall occurs, or the point where the air burbles over the wing rather than flows over the wing. This graph represents a typical wing. Most airplanes have their stalling angle between a 20-degree or 30-degree angle of attack. Now, we know that an excessive angle of attack is the cause of a stall. How do we, the pilots, control the angle of attack of the airplane? Plate 12 shows an airplane in straight and level flight. The control stick is in the neutral position. The elevators on the tail are in a neutral position. Plate 13 shows what happens when back pressure is applied to the control stick. The elevators go up, and this causes the tail to go down. If the tail goes down, the nose of the airplane must naturally go up. Now the airplane is flying at a high angle of attack. If we were to pull the stick even farther back, the nose would raise even more, and eventually the angle of attack would be increased to the stalling point. The only way to recover from a stall in almost all airplanes is to push the control forward, thereby lowering the nose and decreasing the angle of attack. The airplane will then resume normal flight. The elevators control the angle of attack. Pull the stick back, and you increase the angle of attack. Push the stick forward, and you reduce the angle of attack. The elevator control is really the angle of attack control, isn't it? Of course, when you pull the stick back and increase the angle of attack, you are creating more drag, and the airplane will lose speed. In other words, as you increase and decrease your angle of attack, the speed of the airplane will change accordingly. So, along with being an angle of attack control, the elevators also control your airspeed. Destroy any illusions of the throttle controlling your airspeed. Your elevators govern your airspeed. Many people are under the impression that pulling the stick back makes an airplane climb. An airplane will climb when the angle of attack is slightly increased and additional power is applied. Power is really what makes an airplane climb. If you shut your engine off, it is guaranteed that pulling the stick back will not prevent you from gliding earthward. If you're approaching an airport for a landing and you see that you are low, pulling back the stick will only slow you up and allow you to get closer to a stall. When you are low, apply power. Always keep in mind the following rules, and you'll be well on your way to becoming a safe pilot. 1. Control your airspeed with the elevators. If you are going too fast, raise the nose. If you are going too slow, lower the nose. 2. Control your altitude with your throttle. If you are low, add more power. If you are too high, reduce your engine power. Now, there are many case histories of pilots who were too low during an approach for a landing, and instead of adding power, they pulled the stick back and raised the nose in an attempt to gain altitude. Well, when this didn't work, they would pull the stick all the way back, and you can guess the results of that error. By pulling the stick back too far, our ill-fated pilot unknowingly increased his angle of attack to the stalling point. When this occurred, the airplane lost all lift and really began to go down. If he had enough time, our pilot might realize that he should apply more engine power. The throttle goes full forward. The power plant strains to deliver every available horsepower. But our friend persists in keeping the stick in his lap. Well, even with full power applied, an airplane will not fly in a stall. The stick must be pushed forward to decrease the angle of attack. The records are full of stories where a pilot crashed, the engine running wide open, the stick held all the way back in a vice-like grip. Stalls are only dangerous when inadvertently executed close to the ground. A pilot who takes time to learn about stalls will have no trouble from them. Just know what causes stalls, how to avoid them, and how to recover from them should you inadvertently get too close to one. A stall will not occur without warning. First of all, you can't stall unless the stick is held fairly well back. As you approach a stall, the burbling of air above the wings can be recognized by a slight shuddering of the airplane. Recovery is simple. Ease the stick forward and reduce that angle of attack. Applying full power is also recommended to avoid losing too much altitude during the stall. The most important thing to be concerned about is 1. Be able to recognize an oncoming stall. And 2. Remember to lower your nose and diminish the large angle of attack. An airplane cannot stall unless an excessive angle of attack is reached, and will always recover from a stall as soon as the nose is lowered and the angle of attack is reduced. If you're not certain of your ability to cope with stalls, get a good instructor and practice them at a high enough altitude where stalls are relatively safe. Many modern airplanes are equipped with stall warning indicators. These indicators sound off with a loud beep when the airplane approaches a stall. The stall warning indicator is a very simple device. Plate 14 shows a wing with a small metal flap protruding from the leading edge of the wing. At low angles of attack, the relative wind forces the flap to remain pointed downward. Plate 15 shows a wing at a high angle of attack. Notice that in this case, the relative wind strikes the bottom of the small metal flap, and it is pushed up. As the metal flap moves up, it acts as an electrical switch, and a horn sounds off in the cockpit. Stall warning indicators are attached to the leading edge of the wing in such a manner that the metal flap will be pushed up as the stalling angle of attack is reached. This is the end of Lesson 2. If you don't thoroughly understand this lesson, do not proceed. Repeat the lesson over and over until you are sure you have learned it well. When you are ready, take the examination for Lesson 2 in the back of your manual. You are then ready for Lesson 3.